All right, so we're going to be doing the logarithmic function. So the definition of a logarithmic function, so a is strictly greater than 0, and a is not equal to 1. The logarithm, so same rules we put on an exponential function. The logarithmic function with base a, denoted as log base a, is defined as the following. Log of a of x is equal to y. Um, where a to the y is equal to x. And so this basically asks the question, a raised to what power is x? And so this asks the question, I'll write that in here, a raised to what power is x? So log of x, log base, and that's going to be y. And so a to the y is equal to x. So that's the question it's asking. So in order to kind of get used to solving logs, we first need to figure out what it's asking. And so it's nice to convert logs to exponents and exponents to logs. So if we do this, this would be 10 to what power is 1,000? Well, that answer here is 3. Or 2 to what power is 64? Well, that answer here is 6. Or 16 to what power is 4? And that answer here is a half. Okay, so that's what the logs are asking. 10 to what power is this number? And so log base 10 is saying you take the number and you figure out what power this was raised to. Now, here these are all nice even numbers. In reality, you'll have like really long, um, they may not be, and often they are. Here, we can do the same thing here, is I can convert this into a logarithmic function. And so if I do this, the base here is 10. So this is log base 10. I'm going to go to 0.1. And then the power is the answer. So this is 10 raised to what power is 0.1? Well, that's negative 1. Same here, this will be log. Here the base is 5. We're going to take 125, and that's going to give us 5 back. Or no, that's going to give us 3 back. Sorry. And then here we'll have log base 3 of 81. And the 81, 3 raised to what power is 81? Well, it was 4. Okay. So this will kind of get you a little bit of a feel. You'll do some of this conversion in the homework. So let's go ahead and graph this. All right, I have some of these, so I'm going to choose other powers. I'm going to choose 2 to the second power, which is 4. I'm going to choose 2 to the half power, which is a half, or 2 to the negative 1 power, which is a half. I'm going to choose 2 to the negative 2 power, which is a fourth. I'm going to choose 2 to the negative 3 power, which is an eighth. And then I'll choose, I'm going to just choose negative 1. And I'll explain what that is in a second. So here, if we find the log, so log base 2 of x, well here, log base 2 of x is, so of 1, so log base 2 of 1 is 0. So that is 0. Here, if I choose log base 2 of 2, right, if I'm doing 2, when my x equal 2, the answer here is 1. If my x is 4, the answer here was 2. If my x was a half, I get a negative 1. If I was a fourth, I got a negative 2. And if I was an eighth, I got a negative 3. And so the question is log of 2 to the negative 1 is equal to what? And the answer here is undefined. Okay, so log is defined, we'll do this in the next page, only from not including 0, but 0 to infinity, not including the 0. And so this is undefined. So all of this is in this domain. So if I was going to graph that, here, Let's just do log of 2. So at 1 it is 0, at 2 it is 1, at 4 it is 2, at a half it's -1, at a fourth it's -2, and at -3 it's -8. And so it comes in and goes down. Oops. Well, it doesn't actually curve back in on itself. Hi. Ask me how well I can draw today. There we go. And then here, just for fun, I'm going to g of 2x. We already know how to do that. That's here, here. Hold on, that's here, here. Here, and then here. So, and notice, let me use this really light color here. This is y equals x, and so this is a reflection cross. So this is a reflection here, and so these are inverses. Okay, so the log function is an inverse of this function, and I'll let you guys write that all down. Okay. I'm going to open up Desmos as you do that. Desmos. All right. So the next page. So the common function. All right. So logarithmic function with base 10 is called the common log function. Is often written by omitting the base. So log base nothing is really log base 10. The other one is natural log. So log ln of e is log base e. Ln of e is always log base e. Let me put a little warning here. Little warning. Warning. Whoop, whoop. In some places, log of x means ln of x, or natural log of x. So this is true for our book. This is true for our book. At least it used to be true for the book. And this is true in, like, I would say 89% of all cases, right? 89% of all cases, this is true. However, let me actually open, let me see if it's still true. Log. Yeah. Here in Wolfram Alpha, log base e of x is log of x. And so they have that to be their log. And then log base 10 of x is clearly written as log base 10 of x. And so it's not true everywhere. In fact, so just be very careful in where you're looking at, where if it's log, the common log is not log 10, but log e. Just be careful. So in Wolfram Alpha, it says log, it's not log 10, it's log e. The reason I warn you specifically about that one is because that's what we're using for the calculator in this class. So, just so you know, but most places, log base nothing is log base 10. But not all. and not by a large enough margin. I definitely have to I definitely need to write that out for you. So here, I'm going to give you a couple logs here. So I'm going to say log, we're going to do 6, we're going to do 1, or we're going to do 4, we're going to do 1. Let's do that. Let's do 0 0.5, let's do 0 0.25, and then we'll do 0 0.1. Okay, so log base nothing. So we're going to do log, so I'm going to show you log 2 and then log base 10. All right. Log base 2 we already have done. So let's go ahead and graph that. Let me just do the log base 2 real quick. So we know it goes through this point here. It goes through 2 is 1. At 4 it was 2. And then here at 8 it's 3. So this comes in, goes in, goes down. All right, so this is log base 2. Here, log base 10 of 10, well, that's 1. Log base 10 of 1, so 10 raised to what power is 1? Well, it's always 0. So 1, when x is 1, the log will always be 0. It's kind of like in the exponentials when x was 0, it was always 1. Because they're inverses, and so this is true in reverse. And when it's 0.1, it's negative 1. But what happens to the rest of these? Well, these are decimal points. We just plug it in your calculator and get decimal points. So 0.76, 0.6, negative 0.3, and negative 0.6. So, all right. So we have this. And so let's go ahead and graph that. So it still goes through this point. So it's still going through this point. But here, it doesn't hit 1 until we're out to 10. So this is 8, 9, 10. So it's something way over here, right? And then when it's 6, so 1, 2, 3, 4. At 4, it's like 0.6. And then at 6, it's like 0.78. So something here. And then it gets to, and so this is going to come in quite sharply. And then it, here it's already at 0.1, and it ends up going in sharper here too. There you go. All right, so let's show some stuff in. Where do you get those numbers? Oh, these numbers? Here. Da-da-da. I'll show you. So here we're going to have log base 10. So log base 10 of 1. Ask, there's log base 10 of 10. Hold on. Log base 10 of 10 is 1. So 10 raised to what power is 1? Here for 6, you're just going to type in, and this is how you type it into Wolfram Alpha, log underscore your number, and check that it gives it to you correctly. Type in 6 here, I get 7.778. I just rounded just 0.78, right? Put that in. Here, if I plug in a 4, I get 0.60. So I just rounded that out to 0. Here, if I plug in 0.5, and that's how I produce these numbers. Okay, good question. Very, very good question. Glad you asked it. All right, so let's look at it in this decimal for a second. Whoop. All right, so here we're going to have log, not long, log base 2 of x. And that's our log base 2 of x. And then it has the numbers we know. It has 0, 1, or 1, 0, and it goes down to infinity. All right, let's just do log base 10 of x. So log of 10 of x. Okay. There we go. Let's see what Desmos think log is. So if I just say log of x, what do you think that is? See, Desmos believes that log of x and log base 10 of x are the same thing, which is the common thing for it to be, right? And then here we can have log base e of x. Okay, so this is about, remember e is about 2.7. And so notice here it's between the 2 and this. And then here we can also check in ln of x, and notice here that ln of x and log base e of x are the same thing. All right. The other one I haven't shown you is when log, say we have log of 0.5x, it flips upside down. Kind of like when we had the powers would flip upside down, this flips upside down. So here it flips upside down. And notice here as we get, so a couple things to note, as the power of the log increases, it gets flatter and flatter and flatter, right? So here if I have, I don't know, just log of 1,000 of x, notice how extremely flat this is, right? And then it'll just widen out until we have log base of like 1.1 of x. Notice how this is kind of pretty wide, right? This is fairly wide. And so it just, so here's really big numbers all the way up to 1. Here, log base 1. I don't even think that's allowed, but let me see if it'll do it anyways for me. Yeah, it won't do it. It says, yep, that's not a function. Log base 1 is just not a function. So it won't graph it. Technically, it'd be just a vertical line of 1, which definitely breaks the line test, right? The vertical line test, if it is a vertical line, it breaks it everywhere. And then here, if you have like log of, 0.8, notice how this is a little bit more in, and then if I have log of 0.01, whoops, sorry, 0.01, it's pretty sharp, okay? And so here from one, or numbers greater than 1, the logs will slowly bend in this way up to infinity, right? And then when log is less than 1, here we have something really close to 0, and so they'll slowly bend. So here's at a half, or sorry. Oh yeah. So here we'll have them from less than 1 as it goes slowly gets. So here's an eighth, right? Or 8 times or 0.8. Here's 0.5, and here's 0.01. So it bends in this way. Okay. So that kind of gives you a feel of how graphs look and how they do it. And it's good. Good practice would just be type in some numbers and see if it matches what you expect. It's just a good thing to do. All right. So note some of the graphs that have some commonalities in them. So we're going to denote some things that are common amongst all of these graphs that we've been staring at. One, they all have the point 0 or 1, 0. Every log has the point 1, 0. Okay. The domain here is from 0 to infinity. And that makes a lot of sense because the range, so anyway, the range here is from infinity, negative infinity, any number here, we can hit them. Remember that for the exponential function, the range was negative infinity to infinity, and the domain was negative infinity, infinity, and the range was from 0 to infinity. So it makes sense the inverse has those swapped, as you would expect. And then the rest of that, just kind of like what I just showed you there. We'll just leave it at this. Just the larger the A, the flatter the graph. That graph. And if A is less than 1, it goes like this, right? Okay. And so there's just some commonalities. And if A is greater than 1, it looks like this. And we talked about the natural Bayes law. Okay, so I'll let you guys copy that down. And as you do that, I am going to open up one thing real quick. I will just Yeah. Mhm. See if I can find a different one. This one better. Yeah, this will work fine. This will work just fine. Okay. All right, so let's do the last page. All right, so here we're going to talk about some properties of logs. And here, I'll kind of explain where some of this comes from. So here, log base A of 1 is always 0. You know, why? Because A to the 0 is always 1, right? Log base A of A. Why? Because A raised to the first power is always A, right? And this is just the inverse property. This is just the inverse property. Okay, that is basically saying the log is the inverse of the exponential, and the exponential is the inverse of the log, right? So here let's evaluate some of the following. So ln of 1 is 0. Here, if I have log base 3 of 81, well, how am I going to solve this? Well, I want to answer here log base 3 of 3 to, and then I write this to the fourth power, right? 81 is equal to 3 to the fourth power. So now I know this, I can use this property right here to say this is 4. So I rewrite 81 as base 3 to some power, and then I can write that out. So that's technically how you evaluate a log. Here, this uses the cancellation property. So I have e raised to the log of e of x, so this is just x. Same thing here, we're using the cancellation property. Here I'll have log of pi times pi to the 3/4, so this is just 3/4. Okay. Here, log base nothing, which for us is 10, so I'll actually write that out, log of 10 of 10. Well, here I have log of 10 of 10, so this is equal to 1. And here I have log base of 432, which is equal to 1. Well, it doesn't matter. The log of any one of 1 is 0. Okay. So that's just something to use to evaluate these. If it's not any of these, we'll type it in the calculator. I'll show you how to do that for a normal calculator in the next section, but I've already shown you how to do it for Wolfram-Alpha. But let's talk about some engineering applications real quick. The perception of loudness, B, in decimals is a sound given by the following. B is equal to 10 times the log of I over I naught, where I naught is a barely audible sound. Find the decimals of a sound that is 100 times that of I naught. So here, let's just do it first, and then we'll go look at things. Okay. So here, if I want something that is 100 times I naught, so we're going to say I is equal to 100 times I naught. Okay, so that's something that's barely audible. And this is actually what they use, and I'll show you that in a second. So here, I'm going to let b equal to 10 times the log of 100 I naught over I naught. Well, here I can just cancel this, and so this is equal to 10 times, oops, 10 times the log of 100. Well, what is a log of 100? Well, log of 100, well, I can rewrite this as 10 times the log of 10 squared. And this is base 10. So that means, due to the cancellation property, this is 2. So this is 10 times 2. So log of 100 is 2. So this is equal to 20 decibels. Okay. So let me explain why we use a log-based scale. And this is actually how you perceive stuff on a log-based scale. Okay. So let's just look at Wikipedia, right? I figured I'd grab from Wikipedia and anything here. So here, so remember the power ratio. So if it is 0 decibels, right, we have a power ratio of 1, right? Here, if it's 100 times what we have, or so 20 decibels would be 100 times the intensity of a sound. So, and here if we're at 60 decibels, it's 1,000 base, or it's 1,000,000 times the most audible sound, barely audible sound. So this is the system, and your brain actually interprets things this way. And let me see if I have examples somewhere. You can really get into this. All right. So here, normal conversation. So me talking to you, that's about 60 decibels, right? Or ringing the telephone, that's about 80, and a hairdryer or a lawnmower is about 90. And so normal conversation, ringing telephone, and a mower don't sound that much different to you. I mean, it does sound quite a bit. It does sound louder, right? But if we look up here, you know, this would be normal conversation, would be 1,000,000 times more powerful than the slightest inaudible noise. The telephone ringing is 10 or 100 million. Yeah, 100 million. And then the lawnmower is 1,000,000,000 times louder. And so when your ear perceives sound, right, so we're talking orders of magnitude difference, right? But in your head, it doesn't sound like orders of magnitude difference, right? It doesn't feel like you barely hear something and all of a sudden it's like so loud it explodes your head. Your brain actually interprets it in this scale. And for good reason, right? It allows you to use such a broad range of different powers, right? And yet interpret it in a way that you can make sense, right? Because if normal conversation was like so hard to hear, you could have to strain your ears to hear it. And then if someone comes by with a lawnmower and it blows out your ears and you're just useless and you can't hear anything anymore, that would be ineffective. And so evolution, or however you want to say it, um, the way the human mind and ear function is designed is to use a log scale. And we use a log scale in a lot of other things. For those who do videography, you use a log scale and you can press you can press everything, and then you take it out of log scale. That way you can still have info in your shadows, but your brights are not blown out, right? And so a lot of videographies, when they actually film, they film in a log scale. That way when they do editing, it's you have the information in the darks, and you also have the information in your brights without blowing it out. I don't know how many people have done videography, or photography. You can still use the same scale. And so there's a lot of things that use log scale, anywhere from auditory stuff to visual productions. Log scale is very common in engineering. I mean, it's not. It's yeah, I can say it's very common. You may choose a field where don't use it, but a lot of things are log scale. Like I think the Richter scale, isn't the Richter scale a log scale? Let me double check that. Return scale for earthquakes, because I am pretty sure earth. Yeah, here we go. I just use Wikipedia since that's kind of free. Yep. Yeah, and once again here, the magnitudes are log scale. Yeah, Richter magnitude. So these are in logs again. Okay, and so this is another log space scale. So say you're not a sound engineer, right? Um, but you're a civil engineer and you're making buildings. You have to know what you can withstand X amount of earthquake. Well, that's a Richter scale, which is a log scale. So if you're in audio, you'll be doing with that, right? And so it's quite common to see a log scale. And so we use these to express a wide variety of different events with numbers that are relatively close together. And so it's actually a very useful tool. Okay. So that's why we use log. Here's one, Richter scale is another. You'll occur, um, log-based video processing is another. Um, and you can also use it in signal processing. So for those who do signal processing, you'll do that as well. Okay. So logs are very useful. We'll end on that note.